In this video, we discuss an important application of residue theorem, that is Cauchy's residue theorem. This application includes evaluation of certain types of definite and improper integrals. First of all, we will define improper integrals. Improper integral is the integral whose one of the limits is not finite. So that is what we call the improper integrals. So we develop a method to evaluate this improper integrals using Cauchy residue theorem in this chapter. Fortunately or unfortunately, we discuss only the definition of improper integrals and the value of the convergence of that definite integral. We are not going to elaborate on the method in this syllabus. So first we discuss the definition of improper integrals. The improper integral of a continuous function f of x over the semi-infinite interval. Semi-infinite interval means 0 less than or equal to x less than infinity. If that function is continuous over this interval, then integral over 0 to integral from 0 to infinity f of x dx, this is what we call the improper integral. The value of this function is defined to be limit r tends to infinity is integral 0 to r f of x dx. So once this RHS exists, that means the limit of the RHS exists, then we define the left hand side is nothing but the limit of the RHS. Okay, in that case we said the improper integral is convergent. If f of x is continuous for all x, its improper integral over the interval infinite interval minus infinity less than x less than infinity is defined by integral over minus infinity to infinity f of x dx. That is equal to limit r1 tends to infinity integral over minus r1 to 0 f of x dx plus in limit r2 tends to infinity 0 to r2 f of x dx. So if the limits on the right hand side, both limits on the right hand side exist, then we say that left hand side, the integral minus infinity to infinity f of x dx converges. Okay, so these are the quantities to define this minus infinity infinity f of x dx. Next we define the principal value of this integral. Next we define principal value of improper integral. The principal value of minus infinity infinity f of x dx is defined as limit r tends to infinity minus r to r f of x dx. So the convergence is not using this principal value, the convergence is using the limits defined above. That is nothing but limit r1 tends to infinity integral minus r1 to 0 and limit r2 tends to infinity integral 0 to r2. So but we use this limit to evaluate the principal value. The principal value of this improper integral is defined as this limit. Whenever this limit exists, then we can say that there is principal value for this integral. Next we discuss what is the relation between convergence and the principal value. That is, if these two limits exist, then you can write this limit sum of these two limits or limit r1 integral over r1 tends to infinity minus r1 to 0 f of x dx plus limit r2 tends to infinity limit r2 tends to infinity integral 0 to r2 f of x dx. F of x dx can be written as integral over then this, if these two limits exist, then you can easily write the convergence of this these two limits. This is in fact minus infinity to infinity f of x dx. This is the definition. So if these two limits exist, then you can write minus infinity to infinity or the principal value of this f of x dx, that is equal to integral limit r tends to infinity minus r to r f of x dx can be written as limit r tends to infinity minus r to 0 f of x dx plus limit r tends to infinity integral 0 to r f of x dx. That means whenever we assume that these two limits exist, then you can split the principal value as this. So that means whenever the function whenever the improper integral is convergent, then the principal value exists always. So however, the converse need not be true. The next we can see that principal value exists for some this improper integrals, but the limit, these two limits need not exist. So the one implication is always there, but the converse need not be true. For example, consider the principal value of this integral. By definition, this is limit r tends to infinity integral minus r to r x square x dx. That is nothing but limit r tends to infinity x square by 2 from minus r to r, and this is nothing but limit r tends to infinity 0, that is equal to 0, because when you put r the upper limit first and then subtract the quantity obtained by substituting the lower sum, you will get that equal to 0. So the principal value of this integral, this improper integral, is always 0. But if you try to evaluate the limit r tends to infinity minus r to 0 f of x dx, where this f of x is x dx, then in this case we can easily see that r tends to infinity, this integral will be x square by 2 from r to minus r to 0. So this will be limit r tends to infinity r square by 2, but this does not exist, or this is not finite. It is not finite. Okay, so we can say that similarly you can try to evaluate the other limit as well. Limit r tends to infinity integral 0 to r x dx, then you will get or you will reach the same answer, that is not finite quantity. So even though those two limits are not finite, the principal value exists. Okay, so whenever the two limits are finite, then you can easily get the principal value exist, but the existence of principal value is not sufficient to get the convergence. Okay, so this is the interesting fact or interesting relation between principal value of the convergence of improper integrals. Next we describe a method to evaluate improper integrals of rational functions. Rational functions means f of x equal to p of x by q of x. Both are real polynomials. We make use of these polynomial as a polynomial of complex numbers and the Cauchy residue theorem to evaluate the improper integrals. Okay, so the method begins with the identification of all distinct zeros of the polynomial q of z. The polynomial zeros of the polynomial q of z is nothing but the singularities of the f of z, that is f of z equal to p of z by q of z. So the zeros of q of z is the singularities of f of z. So first of all, we identify all the zeros of q of z. In fact, that is the singularities of f of z which lie above the real axis. Okay, we are make use of those singularities, and in fact the residues of that singularities to evaluate the improper integral of f of x. That is the principal value of the integral minus infinity to infinity f of x dx equal to 2 pi I times summation k equal to 1 to n residue of f of z at z equal to zk. So we evaluate, suppose there are n number of singularities, that is n number of zeros for q of z lie on the upper hand side of this, or above the real axis. Then we evaluate all these residues of those singularities and we sum up all these and multiply it with 2 pi I, then that will give the principal value of this. So this is the method to evaluate the principal value of this. So once this f of x is even function, if f of x is even function, then the principal value of integral minus infinity to infinity f of x dx will coincide with the integral minus infinity to infinity f of x dx. Okay, so we can make use of this equation to evaluate the integral as well. So whenever this f of x is even, then you can easily get this minus infinity to infinity f of x dx equal to the principal value. So in that case, you can get this is same as so 2 pi I times summation k equal to 1 to n residue z equal to z k f of z will give the integral value. So this is the method to evaluate principal value of an improper integral.